Hello everyone and welcome back to tutorial 4 of MIE100, the Dynamics course in the University of Toronto. We're back on the topic of kinetics of particles and force, mass, and acceleration. I'm going to be doing another 4 questions for you, and as always, if you have any questions, don't hesitate to drop your question on the comments below or email me. So yeah, stick around. Alright, so let's start with the first question. It's supposed to be an easy, quick one. We've got a 54 kilogram pilot flying a jet trainer in a half vertical loop of 1,200 meter radius. Knowing that the normal force at C exerted on the pilot by the seat is 350 newtons, find the velocity of the jet trainer at C. Okay, wonderful. So, as always, we're just going to reiterate our known values. So the mass is 5 kilograms. Radius of curvature is 1,200 meters. The normal force at C is 350 newtons. And we want to find out the velocity at C. Okay, so what do we know? We know that the tangential acceleration here is constant. And therefore, when we draw a free body diagram, we know that the pilot is going to be sitting upside down. Because the jet moves this way all the way up here. So our guy is going to be upside down. So therefore, the normal force is going to be actually pointing downwards, not upwards. And his weight is also going to be pointing downwards. Now in this case, if you want to know the sum of forces, it's going to be equal to MAN. Now, if we recall Newton's second law, we already know Newton's second law. This is Newton's second law. For curvilinear motion. Now, if we recall what AN is equal to, the normal acceleration, it's v squared over rho. Radius of curvature. And we can find the velocity from this normal acceleration. So again, what is the sum of forces in the normal axis? It's going to be N plus mg is equal to m acceleration, the normal acceleration, which is v squared over the radius of curvature. And then we plug in our known values. And we get Vc is equal to 139.8 meters per second. At the instant under consideration, the cable attached to the cart of mass m1 is tangent to the circular path of the cart. If the upward speed of the cylinder of mass m2 is v2 is 1.2 meters per second, determine the magnitude of the acceleration of m1 and the tension T, in the cable, and what would be the maximum speed of m2 for which m1 remains in contact with the surface? use the values. R is 1.75, M1 is 0.4, M2 is 0.6, and beta is 30 degrees. Okay, as always, you know I love reiterating my known values just to have them in front of me. So radius of curvature, 1.75, M1 is 0.4 kilograms, M2 is 0.6 kilograms, beta is 30 degrees, V2 is 1.2 meters per second, and we want to know the acceleration at 1, the tangential acceleration at 1. We also want to know the tension at the cables, and V2 max. If M1 remains in contact with the surface. All right, so let's get to it. Free body diagrams. So first of all, let's draw the free body diagram for mass M1. We've got the weight, the tension in the cables. First, let's identify the axes. We've got the tangential and the normal axes. Normal force. This is beta. This is the distance from the pulley. And this is also beta. Now, the free body diagram for mass M2 is a little bit more straightforward. We've got the weight and tension on the pulleys. This is the x and the y coordinates. This is the distance S2 to the pulleys. All right, so if we recall the kinematics of constrained motion of connected particles, basically the pulley equations, we know, if we go back here, we've got this length, S1, this length, S2, and this length, also S2. If we add them together, S1 plus 2S2 is going to give you a constant, which is the full length of the cable. If we integrate that to get the velocities, V1 plus 2V2, constant is going to be 0. And the accelerations are also going to be 0. Now, we can find T with this equation. But to find tension with this equation, we need to find other unknowns as well. We need to find other equations to solve for. So this is going to be our first equation to consider. Now we're also going to recall Newton's second law of curvilinear motion. Equation. And that's going to be the sum of forces in the tangential direction is going to be MAT And that is m1g sine beta minus t is equal to m1 at1. This is going to be the second equation. This is on mass 1, by the way. Now for mass 2, we're going to do the sum of forces in the y direction, which is m2g minus 2t is equal to m2 a2. This is going to be the third equation. Now if we solve equations 1, 2, and 3 simultaneously, we can find a2, at1, and t. After plugging in our values and solving the simultaneous equations, we can find a2 is equal to 0.892 meters per second squared. at1 will be minus 1.784 meters per second squared. And the tension T is going to be 2.68 newtons. Okay. Now we need to find V2 max. And to find V2 max, we need to find V1 max first, because that would be easier to find. So this is V1. So to find the critical maximum speed, we need to use the curvilinear motion equations. So an is v squared over rho. The sum of forces in the normal direction is MAN, where N is equal to 0, because this is where it starts losing contact with the ground. Now let's go back to the diagram. We're evaluating M1 here, and we want to know the maximum velocity M1 can reach before it starts losing contact with the ground here. So when it loses contact with the ground, N is going to be equals to 0. And this is what we're evaluating here. So sum of forces in the normal direction is going to be m1g cosine beta, as you can see here in the diagram, which is equal to m1 v1 squared rho. The masses are going to cancel out. Plug in our values. And we get v1 max is 3.86 meters per second. Now we want to find v2 max, this velocity over here. So we're just going to use the constrained motion equations again. This equation this time. So v1 plus 2v2 is 0. That means 3.86 plus 2v2 is 0. And we get v2 max is equal to minus 1.927 meters per second. Okay, so for our third problem, we've got a car. On each tire on the 1,350 kilogram car can support a maximum friction force parallel to the road surface of 2,500 newtons. Okay, so it's parallel to the road. This force limit is nearly constant over all possible rectilinear and curvilinear car motions and is attainable only if the car does not skid. Under this maximum braking, determine the total stopping distance if the brakes are first applied at point A when the car speed is 25 meters per second, and if the car follows the center line of the road. Okay, so what do we know? We know that the mass of the car is 1,350 kilograms, and the maximum force on the brakes is 2,500 newtons each in each tire, so that's times 4. The velocity at A is 25 meters per second, and the radius of curvature is 80 meters. So what's the total distance S that the car travels? Okay, so let's first evaluate the motion of the car from A to B. Let's call this point here point B. This is the linear point. This is the linear distance of the car. So here's A, and here's B, and here's our car. And the friction force is here, 4 multiplied by FB, because there's 4 tires. And we want to find the displacement. So we need to know the acceleration and the velocity of the car to figure out the total displacement. So using Newton's second law, we've got the sum of forces in the x is equal to max, which is minus 4 FB is equal to mca. When we plug in those values, we get the acceleration is equal to minus 7.407 meters per second squared. Now, this is going to be a constant acceleration. So if we recall back to our kinematics of rectilinear motion, for constant acceleration equations, we know that VB squared is equal to VA squared plus 2A SB minus SA. And when we plug in our values, we can get VB is equal to 21.84 meters per second. Now, let's start evaluating beyond point P. Now we've got our FBD here. Of our car moving on a curved surface. So the normal force is going to be pointing this way. Tangential is going to be pointing that way. This is the normal and tangential axes. And our braking force is going to be pointing somewhere in this direction, between the normal and tangential axes. So, if we look back at our curvilinear equations, we know that the total acceleration of the braking force is going to be equal to the normal acceleration plus the tangential acceleration, all squared under the square root. And if we sub in the normal acceleration equation and the tangential acceleration equation, we can get this one here. Now, if we rearrange for AT, we can get 12 squared minus e to the power 4 squared. Now, if you also recall, we know that VdV is equal to AdS. And when we rearrange that, we can get A is equal to VdV over ds. Now, you might be wondering why AT here is negative. This is because the force of the braking force is pointing in the negative direction of the tangential axis. So that's why it was negative here. Now, to integrate that, we can put ds on the other side here and integrate it from 10 to s. And here, we're going to integrate it from VB to 0. Now, to make this integration possible, we need to use our substitution. And we're going to substitute u into v squared. That means dv is going to be du over 2v. That will make our v's cancel out. Leaving us with s minus 10 is equal to vb squared to 0 minus u squared over rho squared. Then we can put the rho squared outside and the half. And that's going to give us minus rho over 2 and if you recognize this integral, this here integrates to arc sine arc sine u over a total multiplied by the radius. Sorry, there's a radius here. I made a small error here. Since we're taking the radius of curvature outside, so it should be included here. And this becomes arc sine u over a total times rho. So let me write it here again. S minus 10 is going to be equal to rho over 2 arc sine u over a total radius of curvature. Now remember that this is supposed to be in radians. So if we go ahead and solve it and plug in our known values, we can get the total distance S is 47.4 meters. Okay, so for our last question of the tutorial, we've got a 5 kilogram block starting at rest on the incline in a system as shown below. A non-constant force F is applied to the block. The contact surface between the block and the incline is smooth and the attached spring mass system is in equilibrium before the force is applied. Determine the block's speed when S is equal to 0.5 meters. Okay, so our known variables, we've got F is 50s plus 100, where S is the distance, so this is a non-constant force. M is 5 kilograms. The stiffness of the spring is 100 newtons per meter. S is 0.5 meters, and we want to find the velocity. So before we delve in, I'm going to be talking a little bit about some new material. Now, this new material might not entirely be relevant, 100% relevant to the question. You might want to solve this question using this new material, but I've solved this question in a different way, just using our normal kinetics of particles equations, so our normal second law equations, but you can also solve it using work and kinetic energy. So this is why I'm going to explain it here right now. So first of all, you want to know the definition of work. Work, or work done, is equal to F T ds, where Ft is the force component in the direction of displacement, and ds is the magnitude of displacement. Now, what about the work associated with a spring? We've got the work done over step 1 to step 2, for example, is going to be equal to F dot dr, where F is going to be minus kxi. X is going to be the deformation of the spring, and K is going to be the spring stiffness. dr is just the displacement of the position vector. And when we plug that in, you can get minus kxi ESI. All right, so this is the work done. Now, what about the elastic potential energy? The elastic potential energy, or VE, is equal to half kx squared. However, the stored potential energy is equal to Vg is equal to mgh, which is the height from the ground. Now we want to find the kinetic energy. So, principles of work, kinetic energy, because they're very related. So, kinetic energy, or T, is equal to half mv squared. And the work done is going to be equal to T2 minus T1, or the difference in kinetic energy. So now that we're done with our new material, we can delve into the question, I mean. First of all, let's start with a free body diagram. Before force is applied. So we know that before force is applied, the spring and mass are in equilibrium. Therefore, the free body diagram will look something like this. This is the normal force, the weight acting downwards, the y and x axes. This is the force of the spring at equilibrium, or S is equal to 0. So what's happening here is the mass is resting on the spring. So this means the spring is compressed. It's not in its relaxed state. It's in equilibrium, so V is equal to 0, and acceleration is equal to 0. However, the spring itself is storing some energy. So very important to remember that. So the sum of forces in the x direction is going to be equal to 0, because there's no velocity or acceleration, it's just an equilibrium. Fk0 minus mj sine 30 is going to be equal to 0. And when we substitute our known values, get the spring force is going to be at equilibrium is going to be 24.53 newtons. Now we want to evaluate after force is applied. After force is applied, the free body diagram is going to look a little bit like this. This is our external force. Distance S, y and x axes, theta. And here, the total force of the spring is going to be equal to Fk naught minus Fk, where this is the force of the spring at distance S. This is when the spring starts to decompress and even stretch. All right. So we're no longer in equilibrium. So the sum of forces in the x is going to be equal to max. We're going to add up our forces. This is just equal to this. So they're going to cancel out. We're going to plug in our values. By the way, this Fk is equal to Ks, which is just 100s. Which is going to give us Ax is equal to 20 minus 10s. Now, if we recall our rectilinear motion equations, we would know that v dv is equal to ads. So if we integrate that from 0 to v and from 0 to s, we can get v squared over 2 we're going to plug in our acceleration. We're going to plug in our known values. That's going to give us a final velocity of 4.18 meters per second. So that was the end of our tutorial. Thank you so much for sticking around. As always, if you have any questions, please leave your question in the comments below, or email me at noor.dawidar@mail.utoronto.ca. And as always, see you next week.